In this video, we're finally going to reveal the submicroscopic model of an ideal gas that gives rise to the ideal gas law. The ideas underpinning the model are known as the kinetic molecular theory, and this is my favorite topic in all of gases, because if you have a good intuitive understanding of the kinetic molecular theory and the ideal gas model, you'll come to appreciate that gases are relatively simple to think about and work with and understand. Much more simple, for an example, than solids and liquids, where we have to take into account some things that we can, to a decent approximation, ignore for most gases. So here we're going to lay out the tenets of the kinetic molecular theory, lay out the assumptions of this model, and take a look at a simulation of the model and see directly by following the gas particles around and measuring gas variables that this model gives rise to the ideal gas law directly. So let's start with the kinetic molecular theory. The kinetic molecular theory is a simple model of the ideal gas that underpins and gives rise to the ideal gas law and explains the properties of gases. And in fact, you don't need a computer simulation to understand how the kinetic molecular theory gives rise to the ideal gas law. The ideal gas law was proven from the tenets of kinetic molecular theory in the 19th century. So this has been known since way before computers came around. The kinetic molecular theory has 5 fundamental assumptions that underlie it. And before we get to these assumptions, I want to actually show you the model so that we can begin to think through some of these things. So what you're looking at is the ideal gas model, a set of particles that obey the kinetic molecular theory, is another way to say it. And we can see that it's a pretty straightforward picture if you look at any given particle. Each particle is moving in a straight line until it collides with another particle or the wall, at which point it changes direction and speed based on the collision. And the collisions are sort of like pool balls colliding, right? Nothing too special there. So we get this collection of gas particles in this box bouncing around. We let it sort of settle down. And the thing I want to draw your attention to is this right here, PV divided by NKT. Now the little k is not big R, but this is a constant related to the ideal gas constant. And N is simply the number of particles rather than the number of moles. Check out that ratio, pretty darn close to 1. From this computer simulation of the kinetic molecular theory, we are already seeing the ideal gas law to a rough approximation pop out. PV divided by NKT, or PV divided by nRT, is approximately equal to 1. And of course, when we scale this up to a mole of gas, it only becomes all the more true. So this is the picture you should keep in your mind when thinking through the kinetic molecular theory and the ideal gas model. And we'll come back to that. It's going to be a very important picture for us to revisit. With that introduction out of the way, let's look at the tenets of the kinetic molecular theory. There are 5. And the first one is that gases are composed of molecules that are in continuous motion. They are in constant motion. They never stop moving. They travel in straight lines in accordance with Newton's laws of motion and change direction and speed only when they collide with other molecules or with the walls of the container. You can see that in the simulation. Assumption 2 already gets us to a pretty interesting point. The kinetic molecular theory assumes that the gas particles take up no volume. This means that every gas particle has accessible to it the entire volume of the container. This can't possibly be true in reality because molecules do take up volume. Matter takes up space, right? That's practically the definition of matter. But it's an assumption of the kinetic molecular theory that simplifies the math, is one way to think about it, and simplifies the way we think about things. The third tenet is that the pressure exerted by a gas results from collisions between the gas molecules and the container walls. So for example, on this simulation, the pressure is calculated using the speeds of particles colliding with the walls and the number of collisions happening in a given amount of time. That's the origin of pressure. Again, intuitive idea, right? When gas molecules collide with the walls of the container, they exert a force. That force over the area of the walls is pressure. Tenet 4 is very interesting. Gas molecules exert no attractive or repulsive forces on one another. This sort of follows from item 1. If gas particles attracted or repelled one another, their pathways would not be straight lines. They would start to curve as they approached one another or got farther apart. And that's not what we see in this simulation, and that is profoundly not part of the kinetic molecular theory, and it's a massively simplifying assumption since we do not need to keep track of the positions of all the particles to calculate a potential energy associated with their positions, say due to electrostatic attraction or repulsion. The potential energy of the ideal gas is zero, and no energy is lost or internalized when the gas particles collide. Their collisions are what we call elastic. The kinetic energy of the particles as a whole is constant, assuming that the box is isolated. It's just redistributed as the molecules collide with one another. Tenet 5 is that the average kinetic energy of the gas molecules is proportional to the absolute temperature of the gas, essentially defining absolute temperature as proportional to the average kinetic energy. This tenet provides a definition of the Kelvin scale on some level. And that's it. These 5 tenets underlie the ideal gas model and give rise to this picture here, which may look complicated as we watch the large collection of molecules bouncing around, but is much simpler than it could be if we took into account things like intermolecular attractions and repulsions, which would cause these paths to deviate from straight lines and make keeping track of the pressure and even on some level the volume an absolute nightmare. The kinetic molecular theory explains the empirical gas laws, not just quantitatively, but in a profoundly intuitive and conceptual way. For example, let's think back to Amundsen's law. Temperature increases results in an increased pressure at constant volume. Why is this? Well, increasing the temperature increases the kinetic energy and thus the speed of the gas particles. We have more collisions and faster collisions per unit time of the particles with the walls, and this results in an increased pressure. Very intuitive. Increase the temperature, increase the molecular speed, increase the pressure. What about Boyle's law? Pressure and volume. Well, as we shrink the volume, as we confine the gas particles to a smaller space, we see more collisions of the particles with the now smaller surface area per unit time, and that's going to result in an increased observed pressure. Smaller volume, greater pressure. That's Boyle's law. Finally, Avogadro's law. At constant pressure and temperature, volume and number of moles are proportional. Well, if I add more particles inside this container and I allow this piston to move, the greater number of particles will be exerting a greater force on the piston. And so the piston will move up and the volume accessible to the particles will increase. The surface area also accessible to the particles will increase, and this is needed to ensure that the pressure remains constant. So the other gas laws, this is just 3 examples, but the other gas laws are likewise explained very readily by the kinetic molecular theory, and thinking about how changing gas variables affects the number and type of collisions happening in a given amount of time.